All right, today we're learning about exponential growth and decay. Okay, so we will have growth or decay. So if we have in this formula positive values of a and b, where the base here of our exponent b is not equal to 1, if our base is a number greater than 1, like 2 or 1.03, etc., we will have exponential growth. Our growth will be above 100%. So we're thinking of 1 here that we're comparing as being equal to kind of 1.00, which is the same as 100%, right? Remember, to go from a percent to a decimal, you'd move this decimal place twice to the left. So 1.00 is equivalent to 100%. Okay, if, however, we're between 0 and 1, remember these are positive, so we won't go negative, but you get a value between 0 and 1, we're going to consider that to be below 100%, like 0.5 to the x power. That would be 50%, meaning we're losing 50% of our value each time. Okay, a value of 0.6 would mean we're losing 40% of our value. We get to keep 60%, 0.6, but we're actually losing 40%. So we call that exponential decay. So growth would look something like this. As we go to the right, it's going to grow. And exponential decay is a value that will get smaller and smaller and smaller and get really, really, really close to 0, but never actually equal 0. So here we can say that's a base of 2, and here a base of 1/2. Okay, what we consider the growth or decay rate is the percentage above or below 100%. Okay, so let's look at what that means with some examples here. So identify each as growth, exponential growth, decay, or neither. Okay, so first thing, in order to model exponential growth or decay, a and b have to both be positive and the base can't be 1. So let's first make sure that they're both positive. That would be a and b. They're both positive, and our base is not 1. Okay, so it's definitely one of them. It's growth or decay. And we're going to look at this base as a decimal. 3/2 is the same as 1.5. So we can imagine this being equivalent to 2 times 1.5 to the x. We are above 1, and that means that this is exponential growth. Okay, then it says identify the growth or decay rate. So let's think about 1.5 represents 150%. Move your decimal kind of twice to the right to find your percentage. So that would be 150%. Well, the growth or decay rate, remember, is how far above or below 100% we are. And since we're above, how far above are we? We're 50% above 100. We are growing at a rate of 50%. So we have a 50% growth rate. Okay, example 2. Let's first figure out if it's growth, decay, or neither. A and b are both positive, so it's definitely one of them. And my base here has a value bigger than 1. So this is, again, exponential growth. Now think about, again, if to convert this to a percentage, move your decimal twice to the right, this represents 225%. But that is not our growth rate. Our growth rate is how far above or below 100 we are. Well, how far above 100 are we? Let's subtract 100. We're 125% above. This is a 125% growth rate. Okay, let's take a look at number 3. A and b, A is not positive, which means this is actually not modeling growth or decay. This negative a value actually tells us, remember, a negative a value kind of reflects our graph upside down. That's what we'd be looking at here. It's actually a reflection of a growth graph, but it doesn't technically model exponential growth or decay. It would just be like an upside down version of a graph similar to this. Okay, so we're going to say neither and then move on. Example 4, they're both positive. And this time our base is under 1, This is exponential decay. And if I move my decimal twice to the right, this represents 84%. Now it is not a decay rate of 84%. Remember, the decay rate is how far above or below 100% we are. Now if we're below, we're going to subtract this from 100%. How far below are we? Well, we'd have to do some borrowing here, but we are 16% below. This is a 16% decay rate. What this 0.84 means is, of this initial value or starting value of 500, every time x increases by 1, we get to keep 84% of our previous value, but that means we're losing 16%. And that's why we call this a decay rate of 16%. We're losing 16% every time x increases by 1. Okay, our next part here, we're going to talk about graphing exponential functions. And we'll just do a couple examples. We'll do more in class. We have kind of a generic parent, which is what we just saw, but we also have a form where we can do our same a, h, and k translations. So here, h is up with x. That's where our function is, up there in the exponent. And k, our vertical shift, is after the fact. So here, b is the value that we're going to kind of multiply our previous x by every time we go 1 to the right. So that'll make more sense as we do examples. A, if I don't have any shifts, if there's no h or k, a, this value in front, is actually our y-intercept. Okay. However, if there are some shifts, it will move from there, but we'll deal with that when we get there. H, of course, is our horizontal shift, and because it's got the minus sign, it's still the opposite of what it looks like, and k is our vertical shift. Now this graph, as we kind of looked at the previous one, and I said this gets closer and closer to 0. By the way, so does this graph if I were going to the left. These actually have a horizontal asymptote. We do have a horizontal asymptote, and that will always be at y equals k. Now in something like this, where there is no k value, you can think of k as being 0, so y equals 0. That's what we saw in the previous two graphs. The domain of this, you can plug in any value for x you want. There are no restricted values, so it's always all real numbers. And the range is just depending if my graph, if a is positive, my graph's going up, so y has to be above my horizontal asymptote of k. And if my graph a is negative and we have an upside down graph, it will be less than, but we'll kind of see that from the graph. So let's say I was graphing this. Obviously we can go to Desmos and type this in. I'm going to calculate a few by hand. So I'm going to plug in 0 for my exponent. 2 to the 0, remember anything to the 0 is 1. So this is 1/2 times 1, which is 1/2, or 0.5 as a decimal. So at 0, we're at 1/2. And notice, because there's no shift here, right? You can think of h and k as being 0 and 0, like minus 0 plus 0. So if there's no shifts, this is my y-intercept. It's 1/2. Okay, let's plug in 1 for our exponent. 2 to the first power is 2, and half of 2 is 1. So 1, 1, right? X of 1, y of 1. Let's plug in 2 for x. 2 squared is going to give me 4, and half of 4 is 2. 2, 2. So our next point. Now we're going to plug in 3. 2 cubed, 2 times 2 times 2 is 8, and half of 8 is 4. So 3, we're up at 4. And let's even plug in 4 here. 2 to the 4th power is 16. And half of 16 is 8. So at 4, we're up at 8. So notice, though, we said this is like my y-intercept, 1/2. And every time we went to the right 1 unit, it's being multiplied by 2 over and over again. So 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. You can see as we go to the right, it's multiplying by 2, just like our geometric sequences. Now, same thing is true if I go to the left. Instead of multiplying by 2, we're dividing by 2. So this would actually be at 1/4, half of 0.5, right? 1/4. And then that would get even closer and closer to 0, like 1/8 and 1/16 and 1/32. And we get a graph that comes in and curves like this. It starts growing very, very fast as we go to the right, and getting really, really close to 0 as we go to the left. So our domain is the set of all real numbers. That's the symbol that represents all real numbers. And our range in this case, because k is 0, it's going to have to do with k. Notice we are staying above y equals 0, so it's y is greater than 0. Okay, let's do a second example. This one has some shifts. It does have h and k. What we're going to do is we're going to start with a graph that just doesn't have h and k, but uses the same a and b. Once we find those points, we're going to do our shifts. Okay, and in fact, let's go ahead and identify them. Here, h, remember, is the opposite of what it looks like. So that's actually +1, which is a shift right 1 unit. And here k, there's no tricks with k on the outside here, k equals -2, which is a shift down 2. So once we get our points, we'll put them on the graph, we'll shift them right 1 and down 2 to get to the final graph. But let's first calculate this. Let's start with 1 as our exponent here. 1/2 to the first power is just a half. And -4 times a half, or half of -4, is -2. 1 -2. Okay, let's plug in 2. 1/2 to the second power is 1/4. 1/2 times 1/2. And 1/4 of -4 is -1. So at 2, I'm at -1. Ooh, looks like we're getting closer over here. When I do 1/2 to the third power, we get 1/8. So I'm going to end up with -4/8, or -1/2. -0.5. Ooh. And in fact, if I continue my pattern, you can see it's kind of being cut in half each time. Multiplying by 1/2, same as cutting it in half. My next value is going to be -1/4, -1/4 at 4. And in fact, if I plug in 0, remember 1/2 to the 0 power equals 1. So this is -4 times 1, or -4. Yep, there's my y-intercept. Remember, y-intercept, value we multiply by every time we go to the right. Okay, now these are not points on my final graph. And by the way, as I go to the left, it's actually kind of multiplying by 2. So I think our next point would be at 8, just continuing that pattern. So here's all the points on this graph if I didn't need to do my shifts, but we do have some shifts. I need to go right 1 and down 2. So we got to move all these points right 1, down 2. Take this guy, right 1, down 2, right 1, down 2, right 1, down 2, right 1, down 2, kind of keeping that halfway mark. And then this guy's going to go off my graph, so we can leave him off. And we end up getting something that looks like this. Okay, and remember, we have a horizontal asymptote, which I should have drawn in our last graph here. This was at y equals 0. This one, my k value is -2, so we have a horizontal asymptote at y equals -2. And we can see that in the final graph here, right? In green, it is curving away from that. So when we go to write our domain, okay, it is still all real numbers, but our range, our y values are staying under -2. So y has to be less than -2. Remember, it'll also never equal it. But that is our final graph in green. So we just graphed the one without the shifts, found our nice points using that y-intercept and what we multiply by to go to the right, and then just do our shifts in the end. All right, our next part, we're going to talk about using compound interest formulas. Okay, so this has to do with exponential growth. This first formula, okay, A stands for the amount that we'll have in there in the end. P is called the principal, and it's kind of your starting amount or initial investment. R is our interest rate, but it must be in decimal forms. You may need to move your decimal twice to the left. In other words, an interest rate of 6% is the same as 0.06. Okay, so this is what we would actually use for R. T is our time, usually in years, or it's the number of times something compounds. And if we need this formula, we use this formula when it's a yearly interest rate, but instead of compounding it once per year, they do it more than one time per year. So that we'll need when we get to example 8 here. All right, given a $5,000 initial investment. Hey, initial investment, That's P. So we know P equals 5,000. And a yearly interest rate of 4.5%. Okay, so here, if I move my decimal twice to the left, we would end up needing to add in an extra 0. R is 0.045. So there's my interest rate in decimal form. And then T, our time in years, they've given us is 10. So T equals 10. So we need to use this first formula if it's compounded once yearly. So A equals our principal, 5,000, times 1. In this case, because it's going up, notice it does say plus or minus, and that really just depends if we're gaining money or losing money. So 1 plus our interest rate, 0.045, to the 10th power. Now, you can simplify this and write it as 1.045, right? We can add the 1 in our decimal. And then this does look more like, we can see, starting value and exponential growth rate of 4.5%. But let's go plug it in our calculator. Okay, so here's our Desmos calculator. We plugged in, and we end up getting $7,764 and about 85 cents. Now, in reality, the bank would not round up for you. They'd usually round off at 84 cents, but we can go ahead and round up. We'll pretend the banks are nice to us for now. $7,764.84. Okay, what about if they're compounding this monthly instead of once per year? Okay, so the only thing extra we need to add in here is we do have an N value. And N is the number of times compounded per year. Well, if this is done monthly, N would be 12. So we need to use this formula if it's compounded more than once per year. So we put in our 5,000. 1 plus our interest rate again, which is still 0.045. This time, though, this is divided by N. So you can see that it's R over N. So over 12 to the N times T power. So 12 times 10. 12 the number of months, or sorry, number of times it's compounded, and 10 our time in years. So let's type this in Desmos. All right, so there we go. So to keep yourself in the exponent up here, when you multiply 12 and 10, you need parentheses, or you can just type in 120. But we end up with $7,834 and about 96 cents. Okay, so as we can see, we made a little bit more money when it was compounded more, right? A little less than $100. But compounding it more times per year than just once actually does make you more money. All right, our last one here. A $9,800 used car loses its value, it's losing its value, at 6% each year. Okay, so we've got a few things. We know P, our starting amount, is $9,800. We know R, our interest rate, will be 0.06. And it's losing value, so that means we're going to need to use the minus in one of these formulas. What is its value 8 years after its purchase? Okay, and it doesn't tell me that this is happening more than once per year, so we get to use the slightly nicer formula here. So A, our amount, equals our principal, 9,800, times 1 minus, this time because it's losing value, 0.06, to the T power. And in this case, T is 8. So another way of writing this, if we wanted to do 1 minus 0.6, that's equivalent to 0.94 to the T power. So you could simplify that, to the 8th power. And let's go ahead and type that in Desmos. All right, as we can see, so I went ahead and left it as the 1 minus 0.06, but you can type in 0.94. And our answer, though, is $5,278 and about 43 cents. We'll round it up and say 43 cents. Okay, there's our answer for part A. Part B says, use the guess and check method to figure out approximately how many years it will take to be worth half its purchased value. Okay, well, first of all, what's half of its purchase value? Let's go ahead and do that first. 9,800 divided by 2 would equal $4,900. Okay, so when will it equal roughly $4,900? Well, this is where we're going to want to go to use Desmos here, and we're going to just play around with this exponent. So I know it's losing value. It needs to be more than 10 years because we're only at 5,200. What about 12 years? Okay, 12 years we've gone past 4,900. So let's go back to 11. And that's pretty close, right? Let's say 11 and a half years. I mean, I would say, you know, we could play around with the decimal here, 11.2. Ooh, 11.2, look at that. Almost 4,900 right on the dot. So a little more than 11 years. And it says approximately how many years. So just kind of playing around with our exponent there, it'll be about 11 years. Okay, so if it says use, guess, and check, we basically just use our formula and we just guess and check how many years, trying to get to our target value. Okay, that's it for now. We'll definitely go through more examples of these things in class, including graphing and our different interest rate types.